Okay. So next week we will talk about like how the exam will be. Okay, so we will have a midterm and then final exam. So we can talk about what kind of questions we will do. So okay, so let's start our discussion for this week. Okay, so what is an eigenvalue and what is an eigenvector? So last week, let us recall what we did last week. Okay, so last week we discussed something called linear transformations. So linear transformations are basically, they are maps between two vector spaces. Okay, vector spaces, if you remember what's a vector space, these are some sets with certain structures on them. They have something called vector addition, and they also have an operation which is called scalar multiplication. So vector spaces generalizes the usual set of vectors we know from high school. Okay, so vector addition and scalar multiplication. So it's a generalization of that idea. Linear transformation is not just a simple map, but it satisfies two important properties. So one is linear transformation must preserve the vector addition. Okay, so if you add two vectors and then apply transformation, it must be the same as first applying the transformation and then adding them. Okay, it must be the same thing. And the other thing is it must preserve the scalar multiplication. So you first apply the scalar multiplication and then apply the transformation is same as applying the scalar product to the application of the vector. Okay, so then we checked some examples whether the given map is a linear transformation or not. Okay, so basically we have to verify these two conditions. If they are satisfied, then the given mapping is a linear transformation. So in some examples, we have seen the answer is yes, and in some examples, we have seen the answer to be no. One easy way of checking whether a given map is a linear transformation is this condition. Okay, so a linear transformation must send the zero vector to the zero vector. Okay, and these two zero vectors can be different because these vector spaces can be different. Okay, but this is not a if and only if condition. So if this condition is satisfied, it does not mean the given map is a linear transformation. Okay, so if it is not satisfied, then it's not a linear transformation. But if it is satisfied, we don't know if it's a linear transformation or not. Then what did we do? Then, okay, we talked about something called standard matrix representation of matrices, right? So what is a standard matrix representation of linear transformations? Well, you take the standard basis, right? So wait a minute, what am I doing? Okay, so standard matrix representation is first of all, what is this thing? Maybe, yeah, standard. Okay, so standard matrix representation of a linear transformation between two vector spaces like this is basically you choose the standard basis, and the standard basis is these vectors are the standard basis. So what are they? What is E1? So I didn't write it anyway. I'm not sure. So what is E1 here? E1 is basically E1 is the vector whose first component is 1 and the rest of the components are 0. And E2 is the vector whose second component is 1 and the others are all zeros. and it goes like this. And the vector En is the vector whose all components are 0 except for the last one. Okay. So these vectors form the standard basis of Rn. Okay. So each of these guys are n vectors. So they are n by 1 vectors. Okay. Or n by 1 matrices. Then we look at the matrix whose jth column is Lej. Okay. So what we do is, so if you are given this transformation, something like this, then this transformation is basically has a matrix representation. Okay. So what you do is you first consider LE1. Okay. LE1 is, you write, you take E1 is the vector. So what is E1 here? So we are in R3. E1 is, oh, okay, I have written here. E1, E2, E3 are these three vectors. So you put in this definition x equals 1, y equals 0, and z equals 0, and you get this column. Okay. So you write the first column, and then you take the second vector 0, 1, 0, and you write it here, and you get this vector 2, 3. Okay, so and you take E3 equals 0, 0, 1, which means x and y are 0 and z is 1, and you get 0 and minus 2. So you get these three vectors. Okay, so I don't know what I did here. Maybe I should erase this part. I was trying to explain something probably. Okay, then, okay, so we did some other examples. So the topic of this week is eigenvalues and eigenvectors. So let me talk about those things, okay? So what is an eigenvalue of a linear transformation? So now we start with two vector spaces again, okay? No, we start with just a vector space, okay? Let V be a vector space. And in this case, if we have a linear transformation from V to V, okay? So let this be a linear transformation, okay? Then, so if there's a vector, if there's a vector x in the vector space V, and such that x is not zero vector, okay? So it's not the zero vector of V, and we have a scalar lambda, okay? In this case, we will assume that this lambda can be a complex number, okay? So this means a complex number. Such that okay, here is the important condition. Let me write this in, I don't know, blue. So L of x equals lambda times x. Then the vector x is called an eigenvector and the number possibly complex number lambda is called an eigenvalue. Eigenvalue of the operator of the transformation L. Okay, so this is the definition of eigenvalue and eigenvector. Okay. So, okay. So example. Okay. So usually we will deal with the case. So we will mostly deal with the case when L is basically a matrix. Okay. L is a square matrix. Let me erase this part. For us, we will usually deal with the case where L is an n by n matrix, okay, and the vector space V is basically Rn. Okay, so usually for us, linear transformations will be square matrices between the space of vectors. Okay, so in this case, the definition of eigenvalue and eigenvector is basically uh, the matrix sends the vector x to a multiple of the vector x. Okay. So for now, I don't want to talk why this is important. First of all, we will see how to compute this, and then I will talk about the importance of eigenvalue and eigenvector. Okay. So our first step is let's try to compute eigenvalues and eigenvectors. Okay, so let's look at a simple example. So simple example. Okay, so one of the important things here is we want this matrix to be a square matrix. Okay, so we can compute only the eigenvalues and eigenvectors of square matrices. The reason is very simple, because if you look at the left hand side, uh, 8 times x. So if this is in general not a square matrix, if this guy is not a square matrix, then this vector has different size than this vector. So this vector will have m components, m entries, and this vector will have n entries. Only in the case where A is a square matrix, these two sides can be equal. Okay. So if, yeah, so we will only look at the, when computing eigenvalues and eigenvectors, we will only look at the case where these matrices are square. So let's look at an example. Let's take A to be the matrix 1 and minus 2 and 1 and 4. Okay, so let's try to find all eigenvalues and eigenvectors. Okay. Okay, so what are we trying to find here? So we're trying to solve this equation, right? A times x equals lambda times x. So what does this mean? This means 1, 1, minus 2, and 4 times a vector x1 and x2 equals the number lambda times x1 and x2. Okay, so what does this mean? If we expand everything here, so let's do it. So left-hand side is basically x1 plus x2. And the right-hand side of the first entry is lambda times x1. And the second entry is minus x1 plus 4x2 equals lambda times x2. So we get two equations. This time we have three unknowns, okay? So we have two equations and three unknowns. What are the unknowns? X1 and X2 and lambda. So we have three unknowns. Okay, let's try to see how the solution works. So let's take these entries to the other side. What happens here is we get what we get 1 minus lambda times x1, right? In x1 parentheses we have the term 1 and minus lambda plus x2 equals 0, and here what do we have? We have minus 2x1 plus 4 minus lambda times x2 equals 0. Okay, so what does this mean? What does this mean? So we have an equation like this: 1 minus lambda, then 1, then minus 2, then we have 4 minus lambda times x1 and x2 equals, in the right hand side we have 0 and 0. Okay, so here we're trying to find non-trivial solutions, okay? There's always a trivial solution of this equation. If I put x1 equals x2 equals 0, then I can always solve this, okay? But the important thing is this non-triviality condition. So we are looking for non-trivial solutions. We are not looking for the zero vector, because zero vector, if I put zero vector here, I will always get, this equation will always be satisfied, because L times zero vector is zero vector. We have discussed this. And right hand side is also zero vector. So we don't want to call the zero vector as an eigenvector, okay? So we're looking for solutions of this other than 0, 0, 0 vector. Okay, so what is the condition for this equation to have non-trivial solutions? Okay, so non-trivial solutions, let me do it like this. The system has non-trivial solutions if and only if and only if this determinant is what? If and only if this determinant is 0, right? So if the determinant is non-zero, then we know that there's a unique solution. So this system will have a unique solution if the determinant is non-zero, because we can always, so if the determinant is not 0, then we can invert this equation and find the solution to be 0, 0, okay? And otherwise, so if this condition is satisfied, then the system will have non-trivial solutions. So let's check this. What do we get? So what is the determinant of this guy? We know that determinant is product of these diagonal entries. And then if we solve this, what do we get? So this will be 4 minus 5 lambda plus lambda squared equals 0. And I can solve this to get what? I will have two solutions from this one, right? So what are the solutions? Solutions will be lambda equals 4 and lambda equals 1. We will get two solutions. Okay, so these numbers are called eigenvalues. So for this example, we found two eigenvalues, okay, and they are real numbers. Did I do this wrong? Lambda square. Oh, I'm sorry, I did this wrong, right? So this will be 6. This will be 6. So what are the eigenvalues? So eigenvalues will be 2 and 3, sorry. Eigenvalues will be 2 and 3. Right? Okay, so once we find the eigenvalues, we need to find the corresponding eigenvectors. So for lambda equals 2, what are the corresponding eigenvectors? So how do we find eigenvectors? So what we do is, in this matrix, we plug in lambda equals 2. So in which matrix? So in this matrix, okay? Or here, I plug in lambda equals 2 and I try to find x1 and x2. So what do we get? So this will become, if I plug in 2, I get 1 minus 2, then 1, then minus 2, then this will be 4 minus 2 times x1 and x2, right? And this will give me what? This will give me 0, 0 solution. Okay. So from here, we can find the solution. How do we find the solution? So let's write the solution in this way: minus 1, 1, and I then put 0 here, and here minus 2, and 2, and 0. So then we do row echelon reduction, right? Row echelon reduction. So how does it work? Basically, the second row is a multiple of the first row, okay? So if I write minus 2 times the first row plus the second row to second row, what do I get? I get 0 and I get 0 here. Okay, so this means minus x1 plus x2 equals 0. Okay, so what does this mean? This means I have only one equation for two unknowns. So I will have infinitely many solutions. So I can call x2 as r, then x1 will be r as well. So eigenvectors, there will be infinitely many eigenvectors of the eigenvalue lambda equals 2 r of the form x1 coordinate is r and x2 coordinate is r. Okay, so as you know, we don't allow r to be 0, because if I put r equals 0, I get the 0, 0 vector, and I explained that we don't want it as an eigenvector. Okay, guys, are you with me? Are you following? Any questions? Yes, sir. Okay. No questions, right? Okay. We're not finished. So we found eigenvectors of one eigenvalue, lambda equals 2. Let's look at the eigenvalues of the other eigenvectors of the eigenvalue lambda equals 2. So this lambda equals 3. In this case, we go back to this matrix and we put lambda equals 3. Then what do we get? So I get 1 minus 3, 1, minus 2, 4 minus 3, right? and then I get x1 and x2, which gives us 0 and 0. So what does this mean? So if I do the computation, I get -2 and 1, and I get -2 and 1. So this gives us x1 and x2 equals 0 and 0. Okay, again, we have the second line a multiple of the first line. So there's only one equation here. And this is, I mean, this is normal because we required that condition, okay, here. So we found lambdas by using that condition. So we don't want two independent equations. If we have two independent equations, the only solution we get will be the 0, 0 solution. So we required that we're not looking for two independent equations. We're looking for just one independent equation. So the second equation is a multiple of the first one, okay? Must be a multiple. So that's normal that we end up with such equations. So in this case, we can easily solve this. So we get only one equation. And again, if I call x2 as, or let's call x1 as r, right? That will be easier to write. Then we get x2 equals 2r. And then the corresponding eigenvectors of lambda equals 3 are of the form what are they? R and 2r. And here we don't want r to be 0. And all other numbers except for r equals 0 are eigenvectors. Okay. Okay, guys. What do you think? Any questions here? Okay, so let's talk about some definitions now. Definition. So in this example, we have seen a procedure to find eigenvalues and eigenvectors, and this procedure, we end up with certain things that we want to give names, okay? In particular, this thing will have a name, okay? It will be characteristic polynomial. So first, let's define that. So let's suppose we have an n by n matrix. Okay, then we define something called p lambda, which is determinant of. So how was this defined? A minus lambda I. Okay, or it's the same thing as saying this is determined. Sometimes it's defined this way, sometimes the other way. Lambda I minus A. Okay. So what is this called? This is called, okay, so this is called the characteristic polynomial. Characteristic polynomial of the matrix A, okay? And the roots of this polynomial gives us the eigenvalues. And this equation is called the characteristic equation, okay? So maybe I should color these things. Where is my coloring? So this is characteristic polynomial, and we also have characteristic equation. Okay, this is called the characteristic equation. Characteristic equation. Okay, so if we go back to the last example, so how did we get this characteristic equation? So this is the characteristic equation of this matrix. Okay, this matrix has the characteristic equation given by this polynomial. Okay, so lambda is just a Greek letter, just like x. Okay, so lambda is the standard symbol for eigenvalues. And the system, so if you look at this, we obtained this equation from this determinant relation. Determinant of this matrix is 0. So determinant is just a scalar. So this is a scalar. I mean, it's a polynomial, but it's a scalar. So if you compute the determinant of this, we ended up with this equation, which gave us this equation. But what is this? This is basically the matrix A minus lambda times the identity, you see. So this matrix is basically same as what? Determinant of the matrix A minus lambda times identity matrix. Which identity matrix? Of course, this is 2 by 2 identity matrix, right? So this is identity matrix of 2 by 2. Because A is a 2 by 2 matrix, I can only subtract 2 by 2 matrices from it. Yes, so that's the way of computing the eigenvalues. Okay, so any questions? No question? Okay, so these two determinants are equal. Basically, one is so these are not. I shouldn't say they are equal, right? Oh, this is not good. This is not good. So okay, let me look at it. So this guy, so this guy, oops. So this determinant is not exactly the same as this determinant. So depending on the size of the matrix, this will be minus 1 to the power n times this guy, okay? Because you see, one is a negative of the other. So if I take the determinant of, so if you recall the relation, so determinant of C times the matrix A is basically, if this is an n by n matrix, this is C to the power n times determinant, right? So do you remember something like this? So this is just a negative of this guy. This guy is just a negative of this guy. So there should be a minus 1 to the power n. But at the end, it won't change this characteristic equation, okay? So the characteristic equation will still be the same, given by this guy. So maybe I should use the notation in the book. I should use the notation in the book and call, so I will erase this part. Okay, so I will erase this part and only call this guy as the characteristic polynomial. Okay, so this will be our characteristic polynomial. Determinant lambda I minus a. Okay, so let me cut this. Okay, so this will be the characteristic polynomial. Let's do one more example about this characteristic polynomial. Let's look at, this time let's look at a 3 by 3 polynomial. Let's take A to be this matrix. 1, 1, 4, and then we have 2, 0, minus 4, and then minus 1, 1, and 5. Okay, so the question is find the characteristic polynomial of this matrix, of the matrix A. Okay, so what is the characteristic polynomial of this guy? So it's defined as in this way. So we defined it as the determinant of lambda times identity matrix. In this case, it will be 3 times 3 identity minus the matrix A. So it will be determinant. What is this? Lambda minus. Okay, I will subtract the matrix A from. So let me write this in detail. Okay. So let's erase this part. So what is lambda I3 minus A? Well, basically this is lambda times I3 is lambda 0, 0, 0 lambda 0, and 0, 0 lambda, minus the matrix A, which is given there, 1, 1, 4, and 2, 0, minus 4, and minus 1, 1, and 5. And the result is lambda minus 1, minus 1, minus 4, minus 2, lambda 4, 1, minus 1, and lambda minus 5. Okay, so we have to find the determinant of this guy. So what is the determinant of this guy? So if I'm trying to compute the determinant, I can do like a column expansion or a row expansion. So let's expand this guy in the first row, for example. Expand it in the first row. So what do we get if we expand in the first row? It will be lambda 1. So let's be careful when writing. So first I consider 1, 1, and 3. The 1, 1 entry is lambda minus 1, and then I write the what is called the minor matrix. So lambda minus 1, 4, and lambda minus 1. So how did I do this? I erase this guy and this guy, right? And obtain this part. Okay. Then I go back, I go to the second entry, and this case it will have 1, 2 entry. So minus 1 to the power 1, 2. And I multiply it with the number there, which is minus 2. And this time, if I erase this one and this one, I get, what do I get? I will get minus 1 and minus 1, and minus 4, and lambda minus 5. Plus minus 1 to the power 1 plus 3. So what do I get? I will have minus 1, lambda, minus 4, and 4, right? Good. Okay, you see it's a lot of work. It's a lot of work. So at the end, what do we get? We get lambda minus 1 times, what are these guys? Lambda times lambda minus 5 minus 4 is 4, and then I will have two minus signs, which is plus sign 2, and this will give us minus lambda minus 5 times minus 4, which is minus 4, and then I will get minus 4 plus 4 lambda. Okay, so this is also lambda, right? Okay, so After some simplification, which I won't be doing here, okay, so I just wanted to show you how it goes. We end up with this cubic polynomial, okay, lambda cube plus 6 lambda square plus 11 lambda minus 6. And the roots of this guy will be eigenvalues. Okay. Let's write this as a maybe theorem. The roots of the characteristic polynomial p lambda equals 0 are the eigenvalues of the matrix A. Good. Okay, so the proof of this theorem really is basically follows from our considerations in this example. Okay, so if you go back to this example and you follow these things, you end up with this thing which is really the characteristic polynomial equals 0 and its roots. So the system will have non-trivial solutions if and only if this determinant, so if the determinant is 0 under this characteristic, so it will only have solutions, non-trivial solutions, which are eigenvectors if and only if these numbers lambda satisfy the characteristic polynomial. So the proof is really hidden in this example, okay? So it's the same thing. Okay, so in the next lecture, we will try to find the eigenvectors of this 3 by 3 matrix, okay? So it will take some time because it's a little bit more involved than the 2 by 2 case. Any questions, guys? Any questions? No? Okay, let's give a break. Let's give a 10-minute break and then we will continue.